In the previous lecture we were discussing about some problems on properties of pure substances, and in this lecture we will continue with some more problems. So, let us look into this problem 1.3. A cylinder piston arrangement contains water at 105 degree centigrade and 85% quality, okay, with a volume of 1 liter. The system is heated, causing the piston to rise and encounter a linear spring as shown in the figure. At this point the volume is 1.5 liter and the given data is that the piston diameter is 150 millimeter and spring constant is 100 Newton per millimeter. The heating continues so that the piston compresses the spring. What is the cylinder pressure when the temperature reaches 600 degree centigrade? Okay. So, let us try to look into this problem carefully. As per custom, let us first draw a schematic of this. So, state 1, I am just copying the property data given in the problem. Then the other data are diameter of the piston is equal to 150 millimeter, spring constant is 100 Newton per millimeter, and state 3 is T3 is equal to 600 degree centigrade. What is the corresponding pressure at state 3? State 2 is the state when the piston just touches the spring. So, when the piston just touches the spring, can you tell what is the pressure? Whatever is the pressure at state 1 at which this is floating, it should be same as that pressure. So, this means that P2 is equal to P1, because the equilibrium pressure will change only after it compresses the spring. Before it compresses the spring, it moves in a quasi equilibrium process, because the resistance does not change, the internal pressure also does not change. Okay. So, then what we have to do is sorry, this is P3. What is P3? So, we have to draw or we have to schematically represent these processes in maybe PV and TV diagram, just to get a good visualization of what is happening. Sometimes without plotting the processes it is possible to get this answer, but I would prefer, as a teacher of this subject with some experience, that if you can draw these diagrams, PV diagram, TV diagram, later on when entropy comes into the picture, then TS diagram, these types of diagrams will give you a good visualization of physically what is the process happening. So, let us try to draw a PV diagram of this. So, PV diagram, state 1. So, what is state 1? It is in the 2 phase region, because quality is 85%. So, it is quality is between 0 to 100%. So, it is in the 2 phase region. So, what is P1? P1 is the saturation pressure corresponding to 105 degree centigrade from steam table, because the substance is water, otherwise you have to look into the table of that substance. Okay. So, I am requesting, please stretch the camera a little bit, because this is not visible. Yes, now it is visible, fine. So, P1 is P sat corresponding to 105 degree centigrade. Then what is that? So, it will be a value calculated from the obtained from the steam table. So, from 1 to 2 the volume increases, but the pressure remains constant. So, it is a constant pressure process. From 2 to 3 it encounters a linear spring. So, because it encounters a linear spring, the pressure from 2 to 3 it will be a straight line like this, with pressure increasing because the resistance pressure is also increasing. Okay. Question is, what is the equation of this line 2 to 3? So, for that all these details are required. So, let us draw the free body diagram of the piston when it encounters the spring. So, now I will not spend much time in drawing the free body diagram, we have already understood how needs to be, this needs to be done. So, mg Pa then there is P0A, the atmospheric pressure P0 acting from here, and there is a Kx, Kx upwards or downwards. So, when this is moving up, it is pressing the spring in the upward direction. So, the spring will apply a force in the downward direction on it. So, Kx, right. Therefore, for equilibrium you have Pa so P is equal to P0 plus mg by A plus Kx by A. So, P3 minus P2 is equal to K into x3 minus x2 by A. X2, right, x3 minus x2 by A.
Is it justifiable to use the symbol X for that?
So,
Conflict with quality.
okay. So, interesting thing is that this x is not same as quality. So, let us put x bar at the top to indicate that it is displacement. So, x is quality and x bar is displacement. So, this one. Now, what is the change in x? That is the change in volume divided by A. So, K into V3 minus V2 by A square. So, to sum it up, we can write P3 minus P2 is equal to K into M into V3 minus V2 by A squared, because capital V, the total volume is specific volume into mass. How do you get the mass? See, at state point 1, you look at the state point 1. So, what is V1? x1 Vg 1 into 1 minus x1 Vf1, right. Sometimes in terms of the steam table notation, this is Vf1 plus x1 into Vg1 minus Vf1, which is also called as Vfg1. Vfg is Vg minus Vf. So, this you get from the table of water at 105 degree centigrade. At 105 degree centigrade, calculate what is V1, what is Vfg1 or Vf1, whatever, any one of these two. X1 is also given. So, this will tell you what is V1. So, what is M? The mass that does not change during the process, that is V1 by V1. Okay. So, that mass you can substitute here. So, and this K you know already, area of the piston is pi d square by 4. So, from here you can write an equation P3 is equal to some A plus B into V3, where A and B are numerical constants. Okay. So, about state 3 what you know? P3 is equal to A plus B V3 and T3 is equal to 600 degree centigrade, right. So, you do not know P3 and V3 independently, you know a relationship between P3 and V3. This is a very unique problem. So, from this combination you have to identify what is P3 and T3. So, what you can do is, if you are doing it manually, if you are doing it by a computerized system, this combination of equations will give you a unique property. If you are doing it manually, you have to make a guess of V3 and you have to, or make a guess of P3, that is better. Make a guess of P3, that P3 will give you what is V3, and then with this V3 comma T3 see whether this will give back to the same P3 or not. In this way you iterate till you make a guess of P3 which is such that converges to the same P3 once you substitute these two. Okay. So, the answer to this is P3 is equal to 193 kilopascal. Okay. So, we will go to the next problem, problem 1.4. A steel tank contains 6 kg of propane, okay, liquid plus vapor at 20 degrees centigrade with a volume of 0.015 meter cube. The tank is now heated. So, this tank is closed. Will the liquid level rise or fall, and what the initial mass is 1 kg instead of 6 kg. So, this is a very interesting problem. You have a liquid plus vapor in a tank and you are heating it. So, what do you expect? You expect that the liquid will become vaporized and water or whatever propane, the liquid here, the liquid level will fall and the vapor volume will increase, right, that is your intuition. This intuition always may not work because you are working in a closed space. Because you are working in a closed space, when the liquid is getting converted into vapor, that vapor increases the vapor pressure within the system. It's a closed system, and that might dynamically alter the state of the system until an equilibrium state is achieved. The equilibrium state may be dictated by the fact that the liquid level despite heating may not fall but actually rise. So, we will look into this very non-intuitive problem now through the property tables. So, let us work out this problem. So, let us call it whatever TV diagram or what. So, I will illustrate the principle of solving this problem before getting into the actual problem. So, there is a very critical data point in the property consideration, that is the critical point. So, this volume, specific volume, is the critical specific volume. Now, we have two possibilities, of course 3 possibilities. One is V equal to V critical, but other than that we have one possibility is V less than V critical, another possibility is V greater than V critical. So, this is possibility 1 or possibility A, this is possibility B. Okay. Now, if you are heating the propane in the closed tank, what is remaining constant? Total volume is remaining constant and mass also is remaining constant. Because the total volume is remaining constant and mass is remaining constant, the specific volume, which is volume per unit mass, is also remaining constant. So, the process here is a constant specific volume process. So, if now you heat this, heat means its temperature will increase, it will move along this path, but if you heat here, it will move along this path. What is the difference? See, as you are heating here, it is going more closer to the saturated liquid line, okay. And once you are heating here, it is going closer to the saturated vapor line. For example, here quality could be say maybe 70% and here it is close to quality equal to 100%. That means here the vapor fraction is increasing, here similarly the liquid fraction is increasing. So, now let us look into the problem data. So, in the problem data you have m equal to 6 kg. It is given that the critical specific volume of, so this is very important, V critical for propane is 0.004604 meter cube per kg. This is given. So, as per the given A and B, actually this is A where V is, so let us see, if M is 6 kg and what is the volume of the tank is 0.015 meter cube. So, what is V1 is 0.015 by 6 meter cube per kg. Maybe it is alright, maybe it is in the liquid state. So, what is this? So, if you calculate this, this will be less than V critical, right. So, it is this state A. If you heat this, the liquid level will rise. Okay. On the other hand, if M is equal to 1 kg, then V2, then your V, V1 dash, the new V for case B, it is 0.015 meter cube per kg, right. So, this is greater than V critical. This means on heating the liquid level will fall. Okay. So, to summarize, if you heat a substance in a closed space, on heating you cannot trivially say whether the liquid level will rise or fall. It depends on on which side of the critical point the volume belongs to. Okay. So, we will work out a last problem. Actually, we will not work it out in full, but we will give you a hint of how to solve this problem. We have solved enough number of problems. So, this is problem 1.5. You have a piston cylinder arrangement, it is loaded with a linear spring and an outside atmosphere. It contains water at 5 MPa 400 degree centigrade with a volume of 0.1 meter cube. If the piston is at the bottom, the spring exerts a force such that P lift equal to 200 kilopascal. It is a hypothetical state. That means, had the piston being at the bottom, that is volume equal to 0, 200 kilopascal equilibrium for pressure will be required to lift the piston. Now, from state 1 the system cools until the pressure reaches 1200 kilopascal. Find the mass of water and V1, final state, and plot the PV diagram of the process. So, let us try to do this. We draw the schematic of this problem. You have water, state 1 5 MPa 400 degree centigrade. See, from now onwards you try to develop an intuition. Since pressure and temperature are given as independent properties, it cannot be a two phase system, and at such a high temperature it will definitely be superheated vapor for water. So, that common sense intuition you can develop without having to look deeply into the table to figure out where is the state point located. So, and the volume is 0.1 meter cube. So, what it says is very interesting, that had the piston being at the bottom, that is volume equal to 0, your P0 P will be equal to P0. P0 is 200 kilopascal. This is not an actual state point, but a hypothetical state point. State 1 is an actual state point where the pressure, volume, temperature, everything is given. Now, the system cools until the pressure reaches 1200 kilopascal. So, when it cools, because it is encountering a linear spring, it should cool along this path only, the straight line joining these two, but the full part of this is not real. It is just a hypothetical set of data points, so that you can generate the direction along which the process will occur. So, the process will occur after cooling from 1 to this point 2, and this P2 is 1200 kilopascal. So, the question is, what is V2? So, how do you calculate this? You use the equation of the straight line, P2 minus P1 by P0 minus P1 is equal to V2 minus V1 by V0 minus V1, where V0 is 0. P2 is 1200 kilopascal, P1 is 5 megapascal, P0 is 200 kilopascal. So, all these are known, and V1 is 0.1. So, from here you can calculate what is V2. V1 is known, you can only find out V2 from here. So, now V2 by V1 is specific volume at state 2 by specific volume at state 1, because mass gets cancelled from both numerator and denominator. So, from here, from superheated table you can calculate what is V1. So, once you have calculated what is V1, you substitute it here, you will get what is V2. That is one of the questions. So, once you know what is P2 and V2, these P2 V2 combination from table will give you what is T2. So, this will enable you to identify state 2. So, you identify state 2 by looking into the combination of P2, which is 1200 kilopascal, and V2 is, the answer to this is 0.01204 meter cube per kg. Okay. So, by looking into 1200 kilopascal and 0.01204 meter cube per kg, you have to identify the state, whether it is 2 phase or superheated or whatever. How do you identify? See, at 1200 kilopascal you see what is Vf and Vg. If this V is between Vf and Vg, it is in the 2 phase region. If this V is greater than Vg, then it is in the superheated region. Then from the superheated table, with this combination you have to find out what is the temperature, and that is one of the questions. So, T2 is 188 degrees centigrade. Okay. So, it is therefore a problem where you will develop a practice of how to identify a state point given not just pressure, temperature, it may be a combination of pressure and volume. With this we conclude this lecture. Thank you very much.